Well, hello everybody, and welcome back to your favorite channel named Bowmaths. And perhaps your favorite channel, not just named Bowmaths, but your favorite channel in general. Well, we are starting a new section in the Fundamentals of Algebra series on fractions. I know that this is going to be a topic that a lot of people are going to need. As someone who's been teaching math for a while now, fractions are one of those topics that they're a lot of students' Achilles heel. They'll learn them early on, but they won't fully understand them, and even into courses as high as like calculus, students will be struggling with them. And it sucks for you because you want to try and learn these new concepts, but you're still struggling with fractions. So I'm going to really take our time with these videos. We're going to go through a lot of different stuff regarding fractions. Some of it will be standard, like, how to add fractions, common denominators, that kind of thing. Other parts of it might be a little more deep than what you normally do with fractions, but I think it's important to do it because then you're going to have a very strong understanding what fractions are. So we're going to go through a lot of theory, a lot of applications, and we're just going to have a great time together. So without further ado, let's get into it. So what are fractions? Well, there's several ways of thinking about what a fraction is. The most common way you'll start by learning about fractions is you think about it as like a piece of a whole. And so what's commonly done is you'll draw some sort of shape, let's say like a rectangle here, and you're going to split that shape up into even sections. So let's say I split this rectangle up into 4 even parts. So what we say is I divided this rectangle into 4 pieces, and let's say I shade in one of those pieces. So then what we're saying is that I've essentially shaded in one piece out of 4. So a portion of the rectangle has been shaded. So we then represent this with a fraction by saying 1 over 4 like that. Or you'll sometimes see it with a vertical bar like this. Both are commonly used, and you'll see me using both of them. So it's important to get used to both of these fraction bar notations. All right, so we say that this is 1/4 or 1/4. If I shaded in 3 pieces, we'd say that's 3/4, right? Or we could also write it like this, or 3/4. So this is one way to think about fractions. And it doesn't just have to be squares, we could do any shape. As long as we're dividing that shape into even pieces, we can say that, okay, well in this case, 1 out of 2 of these pieces are shaded in, so this would be 1 over 2, or half of the fraction is shaded in. So that is our first way of thinking about fractions. All right, so if I drew a rectangle here, split it into 3 pieces, and shaded in 2 of them, what would the fraction be? It would be 2, right? 2 pieces are shaded out of the 3. All right, so that's the first way to think about fractions. Another way to think about them is kind of an extension of this, and it's in terms of proportions. So the idea with proportions is it's basically some piece of the whole, kind of like what we've been doing up here, right, is represented. So let's say I have 10 pens, and 7 of them are blue. We say that the proportion of blue pens is 7/10. 7 out of 10, 7/10. Right, so the proportion of blue pens is going to be 7/10. All right, so let's say I draw some shapes here. All right, so what proportion of these shapes are circles? Well, we have 6 shapes in total, and 4 of them, 1, 2, 3, 4, are circles. So we say the proportion of circles in this situation here is 4 out of 6. 4/6. 4 out of the 6 shapes are circles, so we say the proportion is 4/6. So this is just a more versatile way of thinking about the piece of the whole here, because here we were also thinking about a proportion of the shaded regions to all of the regions of the piece here, right? So this is just another way to think about fractions. And probably the most mature way, or the most abstract way to think about fractions, is just they're a part of a number. Or we can think about them as a decimal, right? So they are a number, but they're kind of like a part of a whole number, maybe you want to say. So if we consider a number line, and I'm just going to go from 0 to 1, and if we split this number line up into 2 even pieces, right? So here we have one piece, here we have another piece. This first piece would be one piece out of the two pieces, so that would be 1 out of 2, or a half. So we'd be getting a half is right here on the number line. If we wanted to think about maybe a third, so what I could do is I could draw another number line, but this time I'll split it up into 3 pieces. So we have 1, 2, 3 evenly sized pieces. So this first segment here is 1 out of those 3 pieces, so we'll call this a third. And then we're adding another one of those 3 pieces, so we have 1/3, we have 2/3 in total, right? So we see that we can put fractions kind of on a number line, and we can think about them as kind of these partial numbers, or these broken numbers. You might also know that we can put decimals on the number line, kind of in between whole numbers. So there will indeed be a way to convert fractions into decimals. Fractions are actually just decimals, just written in a different form, and oftentimes a more convenient form. Let's say you have a decimal that's like 30 digits long. You may be able to write that as a really small fraction. So there's a lot of advantages to fractions, and in a future video we're going to talk about converting between fractions and decimals, but we're not going to be doing that today because there's a different focus I want to look at. But we do see that fractions are just numbers that we can put on the number line here. So we have a few different ways of looking at fractions, and there will be some other ones that I will introduce in future videos. But basically, we can think of a fraction as being a piece of the whole, or we can think about it as saying what proportion out of a total amount something is represented. So what proportion of pens are blue, or what proportion of shapes are circles. And we can also think about a fraction as just being a number, and it's a number that's kind of between whole numbers. And then one other thing to note with fractions is just a little bit of terminology. Let's say I have a fraction like 3/4. There's 2 parts to the fraction. There's the top of the fraction and the bottom of the fraction. And sometimes I'll just call it the top of the fraction or the bottom of the fraction, but there is official words that are used for these pieces of the fraction. So the top of the fraction is called the numerator, and the bottom of the fraction is called the denominator. So in this situation, we'll say that the numerator of this fraction is 3, and the denominator of this fraction is 4. So these are 2 different pieces of the fraction, and it just kind of gives us some words that we can use to refer to the fractions, to discuss them. So keep that in mind, and I'll be using these words moving forward. So the next thing I want to discuss is this idea of equivalent fractions. And to do that, I went over to my friend Kieran's place, I brought some pie, and we shared the pie, and we discussed some things. So I'm here with Vape Memes 2020, and we have a couple of pies. We have a blueberry pie, and we have a mini
blueberry pie.
Also blueberry pie.
It's my favorite.
That's good to hear, buddy.
Thank you.
So we're gonna enjoy a little bit of food and do a bit of an interview here. We'll start with the mini blueberry pie, and we will cut it down the middle.
All right, you want me to do the honors?
Yes, sir. As you can see, the pie has been cut down the middle. It has been cut into 2 pieces. So that means each one is 1/2 of the pie. So I will take a half, and Kieran will take a half, and we will consume. So Kieran.
Yep.
You're a biologist, right?
Yes.
Why is math better than biology?
It isn't.
That wasn't the question.
Yeah, but that was the answer.
Okay, buddy. We're gonna need to rediscuss our answering strategy here. Now, I need you to be mature for me, okay? So, how often do you use fractions in the field of biology?
Well, it'll really heavily depend on what you're looking at, I'd argue. If you're doing, I think if you're doing like some ecology work, it might become a bit more prominent. It's really difficult to say depending on what subject. I mean, I don't think you could really use fractions in taxonomy, like, identifying and naming organisms, at least not much, but...
That's like half a dog over there.
You'd really hope you aren't finding that as a biologist, to be honest.
I mean, but don't taxonomists also discuss like what percent different animals are like related to each other?
Yeah, well, that's basically like phylogeny, like looking at like the relatedness of different organisms, and that does play a bit of a role. I mean, like classic examples are, comparing the DNA between different organisms, and you could say like, this organism has like half of the DNA of this organism is identical to this organism, showing the level of relatedness between the two. And, maybe one organism's like 9/10 of its DNA is identical to this other organism, showing it's even more related.
Right.
Or those two organisms are more related.
So you can see fractions are being used.
Why?
Well, we finished off the pie. Now, we each had a half, which meant we had 2 halves. But holy crap, the whole thing is gone. That must mean that 2 halves equals 1?
I think that checks out,
Oh,
yeah.
baby, that's crazy. All right. So as you'll see, when we started with that first mini pie, it's basically a circle, right, on the top, and we cut that circle into 2 pieces, 2 evenly sized pieces. And we each took one of those pieces. So if we take away 1 piece, that's a half, right? And if we took 2 of them, that would be 2 halves. But we noticed that by taking 2 of those pieces, well, that just left us with the whole pie being gone. So we saw that 2 over 2 was actually just equivalent to 1, right? We see here that we can actually express 1 as being a fraction, right? Where we had 2 pieces and we took 2 of them. So that was the same as just taking the whole thing, right? So we're able to express this whole number here as a fraction as 2 out of 2. So we say that these are equivalent to each other. But we could also imagine, what if we cut the pie into 3 pieces and we ate all 3 of those? Then we're saying, okay, out of the 3 pieces, so 3 is like our denominator, we ate 3 of them, so that's the numerator, that's also equivalent to 1. So we see that we're actually getting all of these fractions will be equivalent to each other because they're equivalent to 1. So we have multiple different ways of thinking about what it means to actually take away the whole pie. We could think about taking away the whole pie as splitting it up into 3 pieces and eating all 3 of those pieces. Or we could think about taking away the whole pie as splitting it up into 8 pieces and taking away those 8 pieces, right? That's 8 out of 8. 8/8 is the same thing as 1. So these are all equivalent ways of expressing these fractions. So now let's continue on with the pie eating experience. So now, this pie here, we're going to cut that into 4 pieces, into quarters. And we're going to each have a quarter. And it's going to be delicious.
Indeed.
Alright, we've cut it into 4 pieces, and we're each going to have a quarter now. I messed up the bottom.
Oh, what did you do?
I'll let you do this. I might have stabbed the bottom a little.
Oh!
Let's do a different quarter.
Are we sure we were going to... Okay.
Oh. Here's my quarter.
Alright. Boom. That's a whole 2 quarters of a pie.
We just took 2 quarters of that pie, but wait a second. Half the pie is missing. That must mean that 2 quarters equals a half. That must mean that 2 quarters equals a half. So for that pie, we split it up into quarters. And if we each took a quarter, we've essentially taken 2 quarters. But that is equivalent to us just having taken half the pie, right? We see that if we remove this piece, half the pie is going to be remaining. So we see then that 2 out of 4 is the same as 1 out of 2. So these are what we would say are equivalent fractions. We're seeing that there's multiple ways to express the same proportion or the same kind of piece of the whole. And we can also think about it as what's half of 4? Well, 2 is half of 4, right? So it kind of makes sense that 2 out of 4 is the same as a half. Alright, so we discussed the pact, and Kieran doesn't want to be fat, so he put the piece of pie back. So we're just going to split this one instead. We're going to cut this one into 2 pieces, Now you could imagine if we cut the whole thing in 2 pieces for each of them, we would have 8 pieces in total. Meaning that here, when we cut this in half, we're going to be having 1/8 of the pie each. But that would mean that 2/8 is just equivalent to 1/4 of the pie.
Yeah, I think that checks out.
No one asked you, Kier. Alright, we each got our 1/8 of a pie now, and in total, we will be consuming 1/4 of it. And then what we did is we just took 1/4 of the pie, and we split that into 2 pieces. So if we kind of think about a pie being in quarters here, and then we want to split all those quarters into 2. So I'm going to just draw a couple of diagonal lines here. So we see that each of these quarters kind of got split into 2 pieces. So now we have 1, 2, 3, 4, 5, 6, 7, 8 pieces in our pie. And then Kieran and I each ate one of those eighths. So in total we ate 2/8 of the pie. But again, notice this right here is just 1/4 of the whole pie, right? So we see that 2/8 is actually just 1/4. So again, these are equivalent fractions. So we say that there are multiple ways to express the same fractions using what are called equivalent fractions. And in fact, there are infinite ways to express any fraction. So the question is, how do we actually convert between these two fractions? And the idea is as follows. If I take some fraction like a half, then what I can do is I can multiply or divide the numerator and denominator by the same amount, and that's going to keep it as the same fraction. So for example, 1/2, I can make that into 2/4 by multiplying the numerator and the denominator by 2. And this will give me 1 times 2 is 2, and 2 times 2 is 4, and we get 2/4. And kind of the reason this works is because when we're thinking about these as proportions, then we're saying that this will be the same proportion because all we're doing is we're just scaling up everything, right? If I take half of a pie, if I just scale everything up by basically doubling the amount of pieces I have in total, I'm doubling the pieces I have in total, and I'm also doubling the pieces that I've actually taken. And so by doing that, we're actually just keeping the same amount as we had in the first place. So if I wanted, I could convert 1/2 into an even bigger fraction. Let's multiply them both by 50. Right? So 1 times 50 is 50, 2 times 50 is 100. 50 is a half of 100, so it makes sense. So we see that a half is equivalent to 50 out of 100. And that also means that 2/4 would be equivalent to 50 out of 100, since they were also both equivalent to a half, right? Now, oftentimes, you're going to want to go backwards with these because the simplest fraction is usually the best fraction to work with. For example, a half, that's easier to think about and more convenient than these two big numbers of 50 out of 100, right? That's a big numerator and a big denominator, so a half will be easier to work with when you're adding things or multiplying or doing whatever you're doing with this fraction. So to simplify, oftentimes we're going to be dividing the numerator and the denominator by the same amount. So for example, let's say I had 10 out of 15, both of these can be divided by 5, right? So if I divide both of these by 5, 10 divided by 5 is 2, 15 divided by 5 is 3, and so we get a much smaller fraction. But again, it's an equivalent fraction because if we multiplied 2 by 5 and 3 by 5, we would get back to 10/15. These are representing the same proportion of things. This is just a smaller way of doing it. So this is a simpler fraction. So we are going to want to basically try and find a method to find the simplest fraction. How do we know if we could actually make it smaller or not, right? Like for example, if I took 10/20, if I divided them both by 2, that would give me 5 out of 10. But then I could divide both of these by 5, right? And that would give me 1/2. So 5/10 is a simpler fraction than 10/20, but it's not the simplest. We could take it all the way down to 1/2, right? It's only because we decided to divide it by 2 in the first place and not by a bigger number that we didn't get right to a half. So the question of how to optimally do this ties very heavily into what we have just been doing with things like greatest common factor and coprimes and stuff like that. So let's look at that. So simplified fractions. So first of all, how do we know when a fraction is the most simplified? For example, we know that a half looks pretty simplified. We can't really make that any simpler because, well, it's just you have a whole and you're taking half of it. How can we express that any more simply? And the reason we can know it's simplified is because 1 and 2, they have no common factors. If they have a common factor, that means we can divide it out. For example, 10/15, we could divide both of these by 5, because they have a common factor of 5, right? So then that gave us 2/3. So these were equivalent fractions, and this is simpler. But then 2/3, 2 and 3, they have no common factor, so they can't be simplified any further. So this is the concept of coprimes, right? Coprimes were two numbers that had no factors in common other than 1. So that means that these numbers are coprime, so it is simplified. So now you see why I was discussing coprimes and all this stuff, right? Because this gives us a nice convenient way to think about fractions. So if the numerator and denominator are coprime to each other, the fraction is simplified. Let's write that down. Alright, so if the numerator and denominator are coprime to each other, for example, 2 is coprime to 3 or 1 is coprime to 2, the fraction is considered simplified. So for example, 9/10, that's simplified because 9 and 10 are coprime to each other. 8/13, that's simplified because 8 and 13 are coprime to each other. 8/12, however, is not simplified because 8 and 12 are not coprime with each other, right? They have a common factor of at least 2. They also have one of 4, right? 4 goes into both of them. So how do we simplify this? Well, we want to divide them both by some numbers to eventually get to a simplified state. So we could start by doing 8/12 and dividing the top and bottom by 2. And that would give us 4/6. But 4 and 6 still aren't coprime to each other. We could divide it by 2 again. Again, dividing both the top and the bottom. If we only divide one but not the other, then we're not actually getting the same fraction. We need to make sure we're dividing both the numerator and the denominator by the same amount. Then we get 2/3. 2 and 3 are coprime to each other, so now we know we've simplified it. But the thing is, we've done 2 steps in here, so there was a more optimal way we could have gone about this if we just divided them both by 4 right away. 8 divided by 4 is 2. 12 divided by 4 is 3. And we get the same situation. And we see that this 2 and this 2 that we took out, 2 times 2 is 4. So we see that that kind of makes sense. But the question is 4, that's a more optimal thing we could have divided by. So in general, what would be the optimal thing to divide by the numerator and denominator such that we get a simplified number in the first step and we're not kind of doing multiple steps here? Well, we're looking for the biggest number that we could divide both by. The biggest number that's a factor to both of them. The greatest common factor, right? So that's where greatest common factor comes in now, right? So we could say that if a fraction isn't simplified, the way to simplify it in a single step is by dividing the numerator and denominator by their greatest common factor, right? Because we're removing the greatest thing that's common in both of them. So that's the biggest thing we'll be able to divide both by without getting a decimal, right? That's the biggest thing they're both divisible by. So for example, 40/60ths. How do we figure out what the biggest thing to divide them both by is? Well, let's find their greatest common factor. So we have to prime factorize them. So the prime factorization of 40 is 2 times 2 times 2 times 5. And the prime factorization of 60 is 2 times 2 times 3 times 5. So the greatest common factor is all the common prime factors. So 2, 2, and 5 are what are common. So greatest common factor is going to be 2 times 5, or 20. So we can divide both of these by 20. And we get 40 divided by 20 is 2, 60 divided by 20 is 3. So we get 2/3, 2 and 3 are coprime to each other, so this is the most simplified fraction. And we didn't have to do it in multiple steps because we went right to the greatest common factor. Now, if you didn't use the greatest common factor, it's not a big deal. You can do it in multiple steps. Maybe you notice they're both divisible by 10 because they both end in a 0, so you divide them both by 10. So then we get 4 out of 6, and then you're like, oh, they're still even, so we can divide them by 2. And we get 2/3, and we get the same thing. But I think it's important to recognize that using the greatest common factor is basically the optimal way to do this, and it's another way to kind of appreciate the utility of greatest common factor and how everything's all very connected. So both ways are fine. I am going to use the greatest common factor method at least a little bit just to kind of get used to it, but admittedly sometimes it is just faster, just kind of breaking off whatever common factors you notice in the moment than finding the greatest common factor. So let's try another one. Let's go with 15 out of 80. All right, so 15, that is 3 times 5. 80, that is 2 times 2 times 2 times 2 times 5. So the greatest common factor is just these 5s. So they have a pretty small greatest common factor, so we'll be able to divide the numerator and denominator only by 5 each. So then 15 divided by 5 is 3. 80 divided by 5, that's going to be 16. So we get 3/16 is the more simplified version of 15/80. Again, the same fraction. This is just a more simplified version, but they represent the same proportion. If we were to take a square, split it up into 80 segments, and shade in 15, that'd be the same thing if we were to split it up into 16 segments of the same size and split it up into 3 segments. All right, so I think that's going to do it for today. We discussed about what fractions are. We can think about them as shaded areas, we can think about them as proportions of things, or we can think about them as just kind of decimals or these kind of partial numbers. And we see that these partial numbers can actually be converted into different versions of themselves. Basically, there's infinite ways of expressing any fraction. But just because there's infinite ways doesn't mean any one of them is great. The most simplified one is usually the best way to express it. And we saw that we can find the most simplified by using theory that we learned in the previous section of coprimes, and then we can figure out those coprimes by using the greatest common factor of the numerator and the denominator. So I hope you found that video interesting. I hope you found it useful and a nice concise explanation to simplifying fractions and what fractions even are. Moving forward, we're going to get into some more complex ideas with fractions, but these ideas that we introduced today are going to be very important and we're going to be using them all the time. So I'll see you in the practice video, but until then, have a good one, stay groovy, and I'll see you in that next video. So, tell me, Kieran.
Yeah.
What's your favorite part about math?
I think my favorite part about math is the eureka moment. When you finally get it, when you finally really grasp the material and understand, like, oh, so that's why we're doing this the way that we're doing it, what have you.
Yeah, and if you keep watching my videos, you're gonna get tons of those moments.
Indeed.
What's your favorite episode of Maths?
So far, I think my favorite's been the Minecraft one. Mainly
that is a popular one.
It's a very good one. What?
Oh, just the worst sound ever.
You know this?
No, stop.
I'm sorry. I'm sorry, that was evil. I shouldn't have done that.
Everyone should go unsubscribe from his channel right now.
Please don't. Actually, I don't think there's enough people to unsubscribe.
To be honest, probably the only common subscriber you and I have is me. Yeah, I'm subscribed to myself. Anyways, you like the Minecraft video?
Yes. I thought it was a very good way of showing how that lowest common multiple could be used to basically predict when certain events will synchronize with one another. I think it's very good for that purpose.
Do you think that's something you might ever use in your biology research?
It's something that's definitely... It's certainly something that has potential to be used. I mean, a great example is different organisms will have different maturation rates. They'll mature at different rates. They'll get to a certain stage in their life at different times compared to others. For example, wheat might grow at a different rate than barley. And so if you have an idea of those sorts of rates and the lowest common multiple, you could actually feasibly get an idea of when to time their growth in order to sync up certain events. If you want to just harvest the wheat and barley all at once, you might have to plant one first and then plant the other so that, they would sync up properly.
Mm-hmm. Fair enough.
So that's more about... That would probably accord better with moving the number line more so than...
True. Which we did discuss in the traffic lights video.
Yes, we did. I saw those edits you made, you bastard.
So So you've taken some math in university. What was one of your favorite classes you took?
That's a tough one, to be honest, because it's like there's a few decent options. I cannot remember the exact name of the class. It was like logic and
Set theory and logic?
yes, set theory and logic. I think that was a really excellent course, not just because of like the. I think it's a good course both because of the math involved and because, well, you know, set theory and logic. The and logic part is surprisingly good in terms of both being applicable to math and potentially other areas of life.
Oh yeah, definitely. The logic that you'll learn in like a first or a second year university class, that gets used everywhere from math to computer science to even like various levels of philosophy. They use that a lot.
Almost certainly, yes.
In fact, most philosophy departments will have a logic class.
Mm-hmm.
Yeah.
Well, it's kind of a necessary thing. If you want to make a good argument, you need like the premises to actually flow to a logical conclusion.
Mm-hmm. Yeah.
So without understanding logic, it becomes a lot more difficult to do that.
Yeah,
So
for
it's-
sure. Yeah, set theory and logic was probably one of my favorite classes when I took it.
Plus, I mean, the last few units of that course were also very fascinating with the concept of greater infinities and such.
Yes. All of which we will cover someday in BOMaths. That's very far away at the moment, but it is within the world of math, so therefore I will touch it
Indeed.
with you together. We'll touch it together. Oh no.